Hello, hello. How's it going? Uh, we are back. Uh, After quite some time, we are back, and I'm sorry for the lighting a little bit today, mm, because yeah, my power cord just broke. But anyways, uh, it just yeah, I think the lighting is pretty good, not bad, and yeah, okay. I guess. Okay, yeah. So welcome everybody to the stream. It's been a long time, and yeah, I went on a vacation. I had a great vacation for almost 10 days, and now we are back. We are back, and I yesterday I was back, and when I was coming back, I was thinking, what can I stream next? What kind of things? Because if you look at my streams, things have been going here and there. I do algorithms sometimes. I do full stack app, but the full stack app is not finished. Then there is also I was looking at some of the things like that I have done. I was also doing some functional, exploring some functional programming using TypeScript. But yeah, so one thing I'm gonna be trying to do from now on is make sure that you know a more proper series is made where I finish off a project before moving on to another. But yeah, hopefully I should be able to stick to that. So I think my camera is a little bit offset. Okay, yeah, I guess so. Anyways, so uh, so tonight what are we doing? We are doing something a little bit unique. Well, not that much unique. We are trying to learn a little bit of C. It's been very long that I have actually coded in C. I coded in C when I was in college, and I never really took it seriously because I was a electronics grad or a CS grad, so it was just one semester, so I had to just somehow pass it. And usually in those things, they teach you data structures. I think, yeah. And you have programs like, hey, if it's a leap year or not, something like that. But anyways, my love for C came back a couple of years back since I found this guy Alexei Kutupov, who goes by the handle of Soting, and he does a lot of recreational programming on low level. So, kind of been learning C from his streams, honestly. It's a very strange source of learning, but his streams has been. I have shared his YouTube handle a lot of times uh, on the live streams, but I'm gonna just share it again. And then there is also, I hope this is what it is. Yeah, sorting. Okay. So these are two of the channels. So daily is basically is his live streams, and the other one is like cutouts, smaller videos that he has. I highly recommend to follow him because he's a great software engineer. He makes really good software. You can get to learn. I'm sorry for the background noise you're getting, but someone's revving their motorbike for no reason right now at midnight. Yeah. So yeah. Anyways, so one of the things which influences me is that he's a wholesome software engineer. Language never really matters for him. Nothing really matters for him except getting a solution. Um, he has a problem, he solves it. So tonight, what are we doing? I am going to start. Uh, I would say I would probably have a couple of streams where the goal is simple to do hash tables. Hash tables are one of the most widely used, you know, um, data structures in C, data structures in daily software. You would find them in caches, you would find them in databases, you would find them everywhere, right? So the main goal of a hash table is a faster lookup, right? So you can have different sorts of tables, but it's usually a hash table where you hash an input, which is a key, and you store a value against it. So hashing is a technique where it gives you a more or less, well, very, very likely it gives you a, a unique identifier against a data set or against a data point. Usually that is numeric. Usually that is numeric. Sorry, I think it's always numeric. Yeah, hashing always would generate numeric. Maybe I'm wrong, but do not quote me on that. Maybe I'm wrong. But usually what I have seen is hashes are numeric, right? And no matter what input you give, it's always going to try and generate something unique. So it kind of becomes a fingerprint. This is also a very terminology that people use. By the way, I am streaming after a long time, and I hope my audio, the music, and everything is correct, and the setup is not messed up. But anyways, if it is messed up, just let me know in the chat. Okay, if you cannot hear me or something like that. So, coming to the point that what we have here is that we have a data point against which we want to store a value. Let's say, as an example, ticker prices or stock market prices, right? So what happens in a stock market price is that you have a ticker, which means, let's say, Cisco is CSCO, Visa is VISI, I guess. I'm not very sure. Apple is APPL. All right. So things like that. Amazon is most likely AMZN. So think of these as unique identifiers for a certain ticker, and this has values against it. So, well, it changes every second, but let's just say that there is a value. Let's take a consideration that what is the end of the trading session value, right? So you would have a value against it. Now, you want a mechanism where you have the key, which is the ticker, which is Amazon, and then you have the value against it, let's say $100, and then you might have Nvidia, which is like $200. You have Microsoft, which is like $150. You would want to quickly get access to it. So you have a list of companies, and the values against them are the end of the trading session values, prices, right? So this is a very classical usage of hash tables. You can take these as a key because these are all unique, and you can store the value against it. Right? So how it works is that, so for that, let's actually do some diagram. And I guess let's start the stream with the live, right? So that we can do some diagrams of how hash tables work. And then we are going to go into coding, and we're going to try and build a hash table tonight. And there are certain other plans to actually how we enhance this hash table, but yeah, those are like follow-up streams and not like most likely not today. Okay, so let's see how much we can achieve. Specifically speaking, I'll be coding in C after a very, very long time. My entire session of C, like learning of C, has been from streams. All right, so that's one thing. So it might take a little while to actually get the coding done. But anyways, let's go live, and I think because I have to reshare it. Okay, I think now it's sharing correctly, and boom, let's move it to that screen. I have two screens now. I always keep saying that because I don't know, I just feel good about it for some reason. But yeah, anyways, So the very first question should be, what is a hash table? What is a hash table? So you have Apple, which is, let's say, $120. Do not quote me on the prices. This is not the point of what the actual valuations are. Then there is Microsoft. I don't know what is the ticker, but let's just say this. Okay, so this is the unique identifier or the ticker from Microsoft. Let's say they are trading at 130. Then there can be Nvidia, which is 150. Then there can also be Tesla, which is like $200. You can have Cisco, which is trading at $70. Well, I know $70. Yeah. Anyways, the numbers are not the actual point, right? So the point here is that, and like this, you would have a bunch of so many tickers, right? I want a mechanism where, given a value, this is the key, and this is the value, right? So given a particular key, I want to quickly look up what is the value. So what is a way to do that? Okay. So let's say these are all the values that I have. 1, 2, 3, 4, 5. These are all the 5 values that I have. Well, one of the ways we can do this is, so if I say MSCT, what you have to do is you have to scan one by one, right? And whatever is the match, that is your answer. So this is an array of key value pairs, and you have a key, which is a ticker, and then you have a value, which is the trading session in price values for it. So what you do is you scan the array linearly, one by one, and if you hit a match, you would return the value, right? So what is the worst case scenario here? Well, the worst case scenario here is that CSC is your search value is in the very end, which means in a worst case scenario, if there are n entries in this array, you have to traverse the array n times. So O of n is a time complexity. O of n is not that bad, but if you're doing this operation multiple times within a millisecond, a second, it kind of becomes a lot of bottleneck because it becomes slow. So we need a mechanism to make this faster. So this is the most naive lookup. Linear search, right? But if you want to have something better, how do you do it? Well, one of the ways to do it is you can sort the array and then do a binary search on it, right? So you can sort the array and do a binary search on it. Well, you have strings in here, we can argue, but let's just say that you can do a binary search on strings too. Okay, it's not just numbers that you're talking about. Well, one of the ways is to, assign these things values. So this is index 0, 1, 2, 3, 4, something like that, right? So once you do a sort, you can do a binary search. So the sorting of the array would be n log n. That would be your worst case scenario. And then a binary search would take this. So this here is your predominant value, or predominant time complexity, right? Which means that if you sort the array every time, so let's say every second I'm trying to get Apple, then I'm trying to get Microsoft, so every time I have to do the sort, right? So why don't we keep the array pre-sorted? If we keep the array pre-sorted, you have to do an n log n in the very beginning, right? In the very beginning, you pre-sorted the array and kept it. And then for every search, you do a binary search, which is coming up to n log. So we definitely improve this. If you can keep the data set sorted, we definitely improve this. But there's a little bit of overhead because first you have to do the sorting. Well, yeah, again, it's all about trade-offs, I believe. So you took a trade-offs and said, okay, I'm going to pre-sort the data. It's going to take some little extra time. It's going to take some extra memory, but that's fine because my lookups are faster than the naive search, right? So, well, this again might be a better search. So sort plus binary search, right? So first we have a linear scan. Second thing, we have a sort plus a binary search. So this was O of n. This is n log n. If you keep it pre-sorted, we can say per operation it's still gonna be n log n. Well, this is an acceptable solution, but then people said, okay, with more compute power, with with more bigger data set, this also kind of becomes a bottleneck. Okay, sorry, this also becomes a bottleneck. So that is when they came up with a genius idea called HashTables, or lookup tables, something like that. Okay, different programming languages have support for hash tables in their standard library in different names. So Java calls it HashMap, Java calls it HashMap, Python calls it dictionary. JavaScript objects are similar to hash tables, but they are slower. So that is why they introduced something called map, which is more optimized for actual lookups, right? So that's one thing. But anyways, it still works as a hash table, right? Associative arrays. I think there is a programming language that I heard of which calls it associative arrays. So you're associating a value to a key in an array. So yeah, that's basically it. But hash tables generally can give you an O of 1 lookup time. O of 1 lookup time means a constant time, means no matter your data set is, like here your data set is 5, or it can be 5 into 10 to the power 9, which is billion. 10 to the power 9 is billion, right? Or trillion. It's billion. 6 is million, so it's billion. Okay. So no matter how your data set is, how large your data set is, if you have done the correct optimizations and if you have done the correct way of spreading the data out, storing the data, we'll come to that, your lookups will be taking O of 1, which means a constant time. So let's say, for an example, it takes 1 millisecond to fetch any one of the values. It's going to take 1 millisecond for every search that you're going to do in any amount of data set. So this is the entire point of having a hash table, right? So this is what the basis of an hash table is. Any questions here till now? I'll pause for a second and then we'll move on of how an hash table works and how we're going to implement, and then we're going to start with actual coding. Okay, so I'm going to pause for a second and yeah, I'm going to see if anybody has any questions. Hey, could you explain it again in brief? Okay. So today we are building a hash table. Okay. So I was just going through the process of what is a hash table and why it is required. So I was just giving an example. Do not go with the values. I was just saying that, okay, given some companies, you have share prices, let's say the end of the session values against you, right? So do not go with the actual values. This is not the actual trading value of Apple and Microsoft, obviously. I don't think so. Microsoft and Nvidia and Tesla, the ticker values are also same. Correct. That's not the point. The point is just I'm trying to explain. Okay. So for me, I only have 6 entries, out of which I say that, hey, can you give me the value of Apple? Can you give me the value of Microsoft? Okay. So these are operations that I want to do. So one of the ways to do that is I store all of these values in an array, and then I do a linear search from here, right? One by one, I quickly go through them. Well, for that particular case, the worst that you can do is your search key is the last one. So you go to the end, you have to scan the entire data set that you have. So currently in this thing, I have 5. So if you do 5, or if you do 5 into 10 to the power 9, it's like 5 billion. If you do that, there's going to be a hell of a difference in the actual time taken, the compute time taken, right? So within 5, it's going to be very, very fast. But if you go to 5 into 10 to the power 9, it's very, 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 very slow. All right. So considering today's modern power, and even before, like, we have better ways to do a search. So that's why I said a linear scan is O of n. It is okay, but it is not great. The other thing that you can do is you can somehow sort all of these. You can somehow sort all of these, right? And you can say that, every time you try to find a value, you sort the data set and then you do a binary search on it. But the problem here is that every time you do a sort, you do n log n, which means it's worse than n. So one of the things you can do is you can pre-sort the data and keep it. So you only sort once, and then you do a bunch of operations of log n plus log n plus log, right? So you do a bunch of operations with that. Well, this is acceptable, but this is also pretty slow. So that is where people came up with a new data structure called HashTables. And HashTable is something which is like, HashTable I think is a generic name. You have hash maps in Java, you have dictionaries in Python. JavaScript object works in a very similar way, but for optimization purposes, you have maps in JavaScript now. PHP, or someone calls it associative array, I think. I'm not quite sure. But the concept of HashTable is that, well, if you're already aware of a big O, right, you already know that O of n means that there is a dependency on the amount of input that you have, a linear dependency, right? Then you have a log n, sorry, then you have a log n. So it again is faster than O of n, but it has a dependency on the number of input, right? But hash tables can give you a lookup time of O of 1. Okay, so this is gonna be constant time, means that no matter how small or how big or how medium sized your data set is, the result is always gonna be given in more or less the same time. We are not going into actual values when we talk in terms of big O, right? So let's say like 1 millisecond is the time taken to do everything, like, compare the key, get the value and return it. Your CPU needs to do something, right? If 1 millisecond is the time that it takes to do, for any number of searches that you do, it's always going to be around 1 millisecond plus or minus some nanoseconds, because CPUs, but it's going to be a constant time. In the grand picture, it's not going to matter. It's always going to be a constant time. So you have an O of 1 lookup time. So this is why hash tables are used everywhere, or lookup tables are used everywhere. They are used in caches. Caches, I think, is the most widely used ones. You can have compilers for doing a lookup on keywords. A couple of other things. Databases most likely you use it. Right? So compilers would be using for looking up their keywords fast. So that is why HashTable is a very widely used data structure. So this is what we discussed till now. Now we're going to talk about how a hash table works internally, what is the concept behind it, and then we're going to start coding. That's the idea. I hope I explained. That's all we discussed. And welcome to the stream. Great explanation. Thanks. Okay. Now, let's do some Picasso level drawings. You can already see that I'm a little bit Tera. I don't know how to say that in English. Tera basically means, I hope Hindi speaking audience is there. Tera basically, like, I always write it this way, right? I don't know why. Even on blackboards, I start writing straight, then it goes like this. But now we're going to do some Picasso level drawings to showcase how actually a hash table works and how it achieves an O of 1 of lookup time, right? The reason why we can do a good drawing is because I'm going to use this. Okay. Anyways. Just bear with me. Just bear with me. So this is an array. Well, no matter what data structure you do, it has to be backed by an array mostly, or you can consider a linked list of pointers. Well, trees are not really linked list of pointers, but you have to traverse through pointers or you have to traverse through indexes, because your RAM is a stick. Your RAM is not like a tree, right? So these are all conceptual structures. The actual data storage behind the scene is mostly linear, and people prefer to keep it linear for CPU caches and all of that. But anyways, that's not the point. Sure, okay, I'll look at it later. Yeah. Okay, so now the entire point is that, so this is an array 0, 1, 2, 3, 4, 5, 6, 7, 8. Let's do some very stupid maths to understand how this thing works. So let's say this is your array where your tickers are stored, right? 0, 1, 2, there are 9 entries right now in the array. If you wanted to do a linear search, what you have to do is you have to start from here and then you have to go through this, right? So let's say that each comparison, because you have to go to each bucket, and you have to compare that, okay, is the value correct? Is the value correct? Is this the value that I'm asking for, right? So let's just say that each comparison takes 100 nanoseconds. It's very, let's just say I don't know, 100 nanoseconds. Let's just say that, okay? Because I think x86-64 has an instruction set called CMP. So I'm guessing, I don't know, just some weird number I've given, okay? Do not go with the numbers. The point is how to understand it, okay? And since I've written nanoseconds, everything will be written in nanoseconds from now. Okay. So now what happens here is that, so let's say that I have to find the value which is stored here. So I have to go here, okay? And also I have to jump through each one, right? Because I will first compare. If it is correct, I return, awesome. But if it is not the one that I'm looking for, I have to go to the next bucket. So let's say that jump, well, that is not the correct instruction set, but just again, go with it. I think it's called incur. I don't know, whatever it is. Let's say it takes 10 nanoseconds. Okay. Again, just go with it. It takes 10 nanoseconds. So the value that you're looking for is stored here. So if you have to take in that way, well, you have to do 9 comparisons. So 900 nanoseconds. And then you have to jump 1, 2, 3, 4, 5, 6, 7, 8 times, right? So always length minus 1 number of times you have to jump. So 8 times is 80. So it is 980 nanoseconds. Okay. This is how much time it would take if your value is here. What if the value is here? This is the 5th index. So you compared 500 slots, 500 nanoseconds, plus you jump 4 times. So 40 nanoseconds, 540. As you can see already, that this value, again, do not go with the actual value, this is just some random value, but what I want to say is this value shows you that if you do a linear scan of your data set, it completely depends on where your value is, which means if you have millions of data, if you have millions of these buckets or array cells and you have to do it, the time taken is going to be huge, right? So let's do a thing where you actually, do a binary search, a sort. So let's say you already sorted it, right? You already sorted it. So that particular pre-sorting, I'm not going to calculate. I'm only going to calculate that when you're giving an input, what is the time that you need to do a search, right? Sorry. So let's say you're looking for a value here, right? So usually, yeah, I think this is the midpoint. So you would go there, you would compare. So one comparison, right? It's not the correct one. Then you have to do a plus minus. So we already said incur is this thing. So let's also say subtract is also going to be taking the same thing, right? Taking the same amount of time, let's say. So you have to first do a comparison. Well, yeah, this is the midpoint. So first you actually had to calculate the midpoint. A lot of things is going on here. You have to do an increment, you have to do a subtract, you have to do a divide. Divide most likely can just be a left shift. So 3 instructions. So let's just say any mathematical instruction is a 10 nanosecond thing, right? So finding the midpoint itself is so let's do a very simple thing. It's plus and then a left shift, so it's 20 nanoseconds. Then you do a comparison of 100 nanoseconds, right? So let's just think in that way. So when you land here, you already took like 20 because you first have to find this. Then you have to do 100, you have to compare. It's not the correct one. So then you now have to figure out left and right. So there's an if-else statement. So technically speaking, on your computer, on your CPU, it has to be jump and all that. So let's just take the complexity down and say, oh, you just did it in 20 nanoseconds. You again found the midpoint. You moved the pointer, then you found the midpoint and all of that. So overall, you can see that to find this particular value, well, here the linear search would be faster. But on a larger scale, it is usually gonna be log of n. Well, you have this, so log of 9. Well, whatever that log to 9 is, right? 3 point something, right? 3 point something, 3.5, let's just say. So here it's always gonna be faster when you do a binary search. Okay. So till now, I hope everything is clear, that we are just trying to understand that if you do a binary search, if you do a linear scan, how the time complexity is, varying depending on where the data is. As an example, right here, well, looking at the data, your binary search time would be greater than a linear scan. Newsflash. And that happens. It completely depends on the data set. But on a larger scale, if I would have had the space and the time to draw 100 million cells, or 1 million cells, and did this entire calculation of how much it is spending, maybe we can write a program. That is a nice idea. Maybe we can write a program where we actually take the data and actually generate the assembly and see how much, and just assign some random values for each individual instruction set to work. And then that's a good idea, right? What do you think, chat? Is that a good idea? It's not going to be actual data related, but the graph, because the graph that we're going to build, that is going to be the correct thing. All right, the slope and this thing is going to be showing the correct data, I feel. So maybe that's a good idea to have a experiment with that. Yeah, exactly. So I'm thinking maybe that's a good idea to stream and to explore. Okay, anyways, sorry. Anyways, let's not digress. Let's come back to the topic. Okay, so now how does a hash table work, right? So let's quickly grab this thing and go here. Okay, so the entire idea of hash table is that the first word is a hash, right? What is a hash? A hash is a unique fixed length string of characters. So I was wrong. Hash doesn't have to be numeric. It can be a string of characters. Thank you. Thanks. And welcome to the stream. Welcome. Savale. Like, YouTube is so stupid. Why do you have a live streaming if you cannot show the names and you show the handles? I mean, Twitch is most likely the better platform for live streaming. But I don't have Twitch set up, and I don't know how many people in India actually would come to Twitch, because most of us use mobiles, and even me, when I spend a lot of time on Twitch, I always do that on my laptop or PC, but never on my Kick. Yeah, Kick is something that I recently learned because I was looking at one of the streams and he was streaming on Kick, but I don't know if Indian people would actually go there. Because most of my viewers on the phone, I don't know how many actually use Kick and Twitch apps on phone. I don't. I use YouTube only. And again, it's kind of a pain in the ass. I have to download it from Twitch, the VODs, and then upload it to YouTube. So I'm kind of lazy in that way. But maybe someday I'll switch to Twitch. But yeah, anyways. Okay. So yeah. So it's acting like a digital. Yeah, that might be an issue. Yeah, exactly. Even it's an issue for me, honestly, right? I don't want to do that. But anyways, okay. So acting like a digital fingerprint that summarizes the original data, making it useful, blah, 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 blah. Hashing is a one-way process, meaning that you can easily get the hash. So hash is a unique identifier for a value. All right. Fixed length and all that is not important right now. What I just want to say is that the main point is hash, and then there's a table. Well, this itself is a table. It's an array of Sadhguru sir. What? Your name is Sadhguru. Nice. Welcome to the stream. Welcome to the stream. How are you guys doing? How are you guys doing? Okay. For a moment, the way you said Sadhguru sir, first of all, don't call me sir. My name is Priyak. You can just call me Priyak. And the way you said Sadhguru, like, I was not understanding whether you're joking. Like, but yeah, welcome to the stream. Okay, coming back to the topic. So this here is a table. So you have the table of data, right? You have the table of data. You have the table of data. And hashing is going to be helpful to find the data in the table. That is where your name of HashTable comes into the picture. If anyone here watching me right now or later, whatever, if you are working with Java, you have something called Jidun Pants. Welcome to the stream. How are you? How are you? Doing great. Awesome. Happy to have you. Welcome. So yeah. So if you are working with Java, you have something called HashMap. You have something called, I think, linked HashMap. It's called linked HashMap. Then there is tree map. Is there any other in the standard library? Okay. Java HashMap collection hierarchy diagram. Give me that. Oh, you only have hash. Well, tree map. Yeah, okay. So you only have these things. Nothing else. Okay. Cool. But anyways, every one of them has a different concept behind it of how the lookup happens, right? So for HashMap or HashTable, the entire concept is that we're going to hash the key. So each key should be generating a unique identifier, which can help us look up in the table very fast. This is what the concept of a hash table is. How do you do that? Well, like it said on Google, that hashing is a function. It can be any function as long as it takes an input and it generates something unique. And technically speaking, you cannot reverse it. So if you get the output, you cannot take the output and push it through another function and get the original value, right? So previously we were talking about Apple, right? APPL. Let's do a very simple, let's just say that there is a function, right? So you pass it through this value, and usually in here, what you try to do is you try to get something, a unique value, let's say 10. So 10 is your hash. What you're going to do is you're going to take, since this is a numeric value, in hash tables we'll always try and generate numeric values. I am not aware if you can do something else, but maybe there is a there are algorithms with which you can double hash and things like that. But here we are just talking about a single hash. Okay, so you pass it through a function and the answer that you get is 10. So this is your unique identifier, a fingerprint for the value of Apple. Now, what can you do with this value? we can say that let's put the value again. So Apple was, I said, $120. It's trading at $120 today, right? So we are going to take the value 120 and put it in the 10th index. Can we do that here? We cannot, because our table, our array is of the size 9. So we don't even have a 10th bucket. Right. So how do you do that? Please explain the arrays. So arrays is just a linear or contiguous memory blocks where you store same kind of data set, data types. So program is, so I would say you can go here and just check where is, yeah, you can go and check this, because if I go into arrays right now in depth, it's already like an hour that I'm yapping and not doing actual coding, and I want to get into actual coding. But yeah, so in arrays in general is just a contiguous block of memory where you store the same type of data. Okay, so this is what an array is. Okay, so if you take in terms of 10, so it doesn't have an index of 10. So what do we do? Well, usually what happens is that you try to fit this 10 into this particular bucket. The question is how? Well, the very simple answer is let's, wrap it up. And wrapping it up is nothing but doing a mod. So if you do 10 mod 9, which is the size, you would get 1. So Apple goes in this bucket. Then there was CSCO. So this is 11, let's say. This generated 11. If you do this, mod 9 is gonna be 2. So where is this? So this goes in this bucket, right? So what happens is that you have to do a hashing of this particular input, get a value, mod with the length of your hash table of the backing array, and just take the bucket. That is all. This is why your lookups are very fast. You don't have to go to each and individual place. Even with binary search, right? You are doing less number of comparisons, but you have to still compare log n number of times. Here, we don't have to do that. Here, we are generating unique IDs for that particular key, and we are storing values against it so that when we are retrieving, we can just do the same thing. Because the moment I say, can you give me the value of CSCO? You pass it to the function, you get 11. You mod it with 9, you get 2. You immediately go here and say, hey, give me the value. There is no comparison. There is no comparison that is this bucket storing the same value? Is this bucket not storing the same value, right? So this is what the general idea of a hash table is. With each key, the key can be anything. You pass it through a hash function, you generate a unique ID. Well, if that ID doesn't fit, usually it doesn't fit. So you can do a wrapping around. You can just mod it with the length of an array and get a bucket. Well, these are called buckets or cells, right? So you can just get a cell, go to that place and say, give me the value. So this is why it is always O of 1. It is always O of 1. Thank you. Okay. So is the idea of how a hash table works? What is the main idea of an hash table? And how this entire algorithm works? Any questions here? I'll take a quick break. But yeah, if any questions on the chat. Okay, well, there should be a question here. What is the question, or do we see a problem in this particular algorithm of how a hash table works, right? A hash table works in a very simple way. You have an array, and then you have a key. You pass it through a hashing function. You get the hash. So the length is n. You just mod it with n. You get the index. You go to that index and you store the value. This is how you do it, right? This is how you do it. Any problem in this particular way? Any problem? Well, there's a single problem. What if two keys somehow end up being in the same index? Right? The problem here is that, let's say, key 1 is generating a hash of 11 and key 2 is generating a hash of 2. You mod it with 9, taking our previous example. This is 2. You mod it with 9, it becomes 2. So both of these together will be going in this particular cell. How do you work it out? Well, this is what is called a hash collision. Well, even though we call it a hash collision, it doesn't have to be that the hash is same. Like I showed you, the hashes are different. But since you are wrapping it around and putting it in a array, that's why this issue comes up. So how do you fix this particular part? Well, there are two strategies to do it. One is called chaining, and one is called, I think, open addressing or probing something. I don't quite remember the terminologies, but yeah, something goes like this. So what is chaining and what is open addressing? And we are going to be exploring both and trying to do a benchmark of how things work. Well, one of the things here is that chaining is, instead of this being a bucket of the type key value, this is a linked list. This is a linked list. So what happens is that when you land on the same bucket, you first say, oh, there's a value here. Let's add a node. Let's add a node. Which means that is why I said O of 1 lookup time is amortized or an average, because, well, if you land on a bucket which is a linked list and there are k keys in here, your time complexity increases to a linear search within that, right? Well, the only thing here is that you don't have to go through a million keys. You have to go through a lot less number of keys, because if your hash function is good enough and your array size and everything is good enough, you will have less and less collisions, which means that the length of the linked list would be less. So that is why it is still said this is O of 1, but amortized. Amortized basically means how I understand amortized meaning is most of the times. Okay. Yeah. So this is what chaining is. So you have a linked list. Instead of having a cell, you have a linked list. Then there's another strategy called open addressing, which is basically you find this particular cell to be taken. So what you say is, hey, why don't you look at the next bucket? Well, technically it shouldn't land on 3, but well, what can you do? You have to say, hey, 2 is already taken. Can you see 3? Is it good? Once you see 3, it's taken. Okay. Can you see 4? So you go +1 always. This is a linear probing, if I'm not wrong. So you go one by one. And whenever you find an empty slot, which is the hole, you push in your key in there. Right? So this is how, this is how it usually works. There are different other strategies where you can have quadratic, I think it's called. So you say you do a +1. If there's no hole, you say +2, then you say +4, +8, something like that, right? And of course, you have to wrap around and things like that. But yeah, these are the two main strategies that we use to take care of hash collisions. There's a very interesting thing in here, but the problem hash collision, I don't quite know what this is called. Not birthday attack, birthday paradox. So Jonathan Blow has a really good the birthday problem, I think. Yeah. So it's called the birthday problem. You can Google it up, the birthday problem. Why finding a hash collision is easier than expected, similar to just how 23 people have a 50% chance of blah 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 blah. Not interested in that, meine Freunde. I'm interested in Blow birthday problem. Jonathan Blow HashTables. I'm not quite sure which one. Yeah. I'm pretty sure this is the one. So this particular video I would highly recommend because it's quite good and it actually gives you an insight of how hash collisions are, mitigated and what is the things. Dude, why did my okay, my bad. Okay. Yeah. So this video I would say is pretty good in knowing how what is hash collisions and the different strategies that people took up to actually resolve it. So I would highly say that, hey, please go ahead and listen to that particular talk and that particular session. But yeah, so what is the goal for today? So any questions about how a hash table works? What is a hash collision? What are the different strategies that you do to resolve hash collisions? Things like that. Any questions still here from anyone about this? Okay, I guess not. So, what is the goal that we have? One second. Open up my. Okay. So, what is the goal that we have? Well, the goal is very simple. We are doing a hash table in C. Okay. And we yapped for almost an hour. We yapped for an hour. So it's time to actually start coding. We'll do a hash table in C. So the very starting we'll do is string versus an integer, or like size t, something like that. Like let's just say integer. So strings are going to be the key and then integers are going to be the value. So we'll take up a particular text and see that if we can get the count of the words there correctly. Right? And yeah, that's basically it. And the second thing that we want to do here is that for hash collisions, this is one. Uh, this is the second thing. The third thing is that we are going to be doing chaining as part of linked list, as part of hash collision uh, resolution or resolving hash collisions. So we're going to be doing that. So if I just quickly note down, because my handwriting is so good, like I said, it's like Picasso. If you're going to be jotting down things that we're going to be doing, only if VS Code opens fast. So hash table is just going to be a string to an integer, and linked list for each bucket for hash collision resolution. And then we're going to get some text from the net and do a word count. That is gonna be most likely the goal of today. Well, we already discussed what a hash table and all that is. I would like to get into a core, I would like to get into coding right now. Okay, but we are not gonna stop here. Well, not for today. This is the goal for today. Let's see how much we can get it done. It's already 12, but we'll try to get the entire thing done. The goal here is that next we are going to take up something very, very weird. I don't know if we can do that, but we'll try to see. So if anybody here knows about Java, so recently with Java 8 or 9, they moved from linked list to red black trees when I think the number of nodes crossed 64, if I'm not wrong, some number, right? So we will learn how to do a red black tree and implement it. This is a really, really big thing. If I can do it, I would say, oh my God, like I would praise myself, because this here is one of the most challenging data structures I feel till now in my life. I have never implemented it. I have just read about it. I have to go through the internals. I have to go through how to implement it and all things like that. So I don't know how easy it's going to be. I'm pretty sure it's going to be very, very difficult, but it's also going to be pretty fun to do this. Okay. But then we are also going to do open addressing, linear plus quadratic, and we are also going to Google up, how, like, what are the different other strategies that you can do for open addressing, or I think it's called probe, something like that, open probing, I don't know, whatever. But the ultimate goal of this particular series is gonna be make key value generic. Let's see. Yes, this is what it's gonna be. But this is technically gonna be 7. I'm also gonna do some benchmarks here and see which one is better in which cases. So this again, like I might have to, move this down, because this would need something like Valgrind, perf, I don't know, some other benchmark tools that we need. So we'll try to optimize this, and we'll try to understand that how we can, what kind of different inputs make is good for different kinds of hash functions, different kind of probing techniques, right, or chaining techniques. So this is what the goal is today. Well, the goal today is just this. Okay, and yeah, we'll make a quick short break of 5 minutes, and then we're gonna get started on this. Okay, so yeah, I'll see you in 5 minutes. Okay, we are back. We are back. And uh, yeah, we are back. And we're going to start coding now. So it's already 12:30 in the night for my time, but we're gonna grind through this. So we're gonna make an hash table, and okay. So the very first thing is, what do we call this particular project? All right. So what I'm thinking is, let's call this hash table. Okay. Uh, why is my terminal slow? The heck? Okay, something is off with my terminal. Why is it slow? I don't know. I guess I have to update it. Do I need to update? Do I need to update this? Is it update? Okay. Hopefully it doesn't mess up my stream. But I'm not updating the kernel, that's for sure. Something is really off. Okay. So, add.c include, I think how you write it is like this, right? Hello world, and that's how you do that. So let's make a make file, and we're gonna say this is hat, which depends on hat.c. So this is cco hat. क्या हुआ? बाहर हुआ शायद. Okay. So I think all warnings, extra warnings, and then पीछे ये तुम्हारा pedantic gtp hat.c. Okay. So if you do that, it says hello world. So our setup is working, and it's working, and it should be fine. Now, one of the things I was looking at is that there's also a way where output can be S, I think. Which is an object file. Yeah, so so how do you do that there? Is it assembly? Okay, it's assembly. And specifically x86-64 assembly, which I have no clue about, but this I feel can give a lot of information of optimizing things, right? So yeah, we will look at that later on. So this is fine. What we're going to do right now is, so we're going to do a single header file style library, I think. So if def, not here, I believe. So okay, anyways, let's start building the hash table, right? So we need a bucket because we are doing chaining. We need a linked list. So each linked list has to be a key value pair, and we are doing for strings specifically, right? So let's do this thing where we say, how do you do that? Type def, I think you do it like this, right? Struct here, this is gonna be, so let's call it an entry. This is exactly how Java calls it. So I'm gonna call that, and this here is gonna be key, and I think there's something called size t, which is value. Okay, so that is that. Well, yeah. Now I think does it work? No, I don't know why my tmaps is not working. But anyways, maybe I can have a separate terminal just to get it working. Okay, hopefully it comes up. Okay, cool. So you have an entry, right? You have an entry, and one of the things we want to do here is we need a linked list. We can ignore the linked list by saying type def struct. So here entry, so it's a pointer, it's a single pointer actually, right? It's a single pointer, and well, the entry should be having, is it a doubly linked list? I think it's a doubly linked list because deletions would be faster then. So I think what you have to do is entry, right? Because, okay, so let's go back actually, because as far as I remember, you cannot do entry next and entry previous. Yeah, so it doesn't know. So I have to redefine this. How do we do that? I forgot. Uh, C redefine type def. How do I predefine it? Forward declaration. Oh, you say this is a structure. Then you define the structure. Aha. Okay. Struct entry. Then you can simply say entry, and then you can say struct entry. It's this, and here you can just say that. Size is unknown. I think it's in the standard lib. Is that okay? But it says okay. I don't have a main, so I cannot run it because uh, I'm trying to build an executable out of it. Okay, that is fine. That's fine. But here now, we need to say type def struct. Here, this is a hash table, and here it has to get entry. Then it has to be a size t. Size t capacity. Okay, so now if I do a make, so should work. Still complains about this kind of thing, but that's fine for now. It's fine for now. Okay, so we need a function which would initialize the thing in here, right? So so I think we need a configuration, but I suppose we're going to refactor it later on. So right now we can say it gives a pointer to the hash at new, where I would say that you give me size t capacity. Let's just do default stuff for now, right? Let's just do default stuff. And in here, I am going to say that we need to allocate the space. So size t capacity is 16. Okay. Size is 0. So we need to do malloc. As far as I remember, malloc is the one to do this thing. So yeah, you just have to say this, right? So in here, you have to give it a size. So you have to first initialize the entries. Then you have to initialize this. Well, not really, not really. Hopefully these would be zero initialized. So if I just go to malloc and I say the size of hat and take this return, I think this is gonna be correct. Well, this is not correct. Okay, you are expected. Oh, okay. Okay, it's unused, so we can. My bad. Okay, cool. Well, we are not going to right away return it. So we're going to say hat. Hat is this. Then I'm gonna have to say hat size is 0, hat capacity is 16. Then I'm gonna return hat. Cool. So let's see. So here I can say int main void, and here that is and new and printf hello world. Okay, so I suppose I'm just gonna say add new with add init. Array, why did it not work? Query is cute. Not sure. Okay, I don't remember win commands. Awesome. So I'm just going to say this is init. So this is also init. Okay. So now let's make a unused variable. It's complaining. We can just say void hat, make the compiler happy. Printf, you have to say include stdioh. Okay. So now this works. Awesome. So one of the ways to look at this is I don't have gf2, I suppose. Yeah, I don't have gf2 installed, so I'm just going to use gdb at. Okay, and I'm going to say break at main UI enable. So here I'm just going to say run. Why is it stuck? Something is off with my what the heck? Okay, I don't know what is the issue. Anyways, so it's here. I'm gonna step over. So we are here now, And now I suppose what we can do is print hatch. So this is a pointer. This is the pointer. But if I say hat like this, okay. So entry is null. Entry is null. Size is 0. Capacity is 0. Okay. So if I say hat of 1, man, doesn't support read line things. Okay. Hat 1. So how can we do that? Is that how you do it? Huh? I'm not quite sure how I do that. Okay. But then I can get to next and things like that. Since hello world, blah blah blah. And can I just exit? Yes. Okay. For some reason, my prompt is very slow today. I don't know what is wrong. But it seems to be, maybe we can quickly install GF2. So if anyone is interested, it's a front end for GDB, and do I wanna? Oh, there's a build sh. Understandable. What are you talking about? What is this right here? What if I do this? Everything looks to work good. Okay. Okay. Is that it? Ooh, my goodness. Okay. So we were able to build it. Okay. Uh, if I just copy this thing, I should have do I not have a bin in here? I do have a bin. So what if I just copy third party gf2 gf2 to home bin? Okay. Can I just do gf2? Oh, boom. Okay. So yeah, I think I have to do gf2 hatch. Okay. Wait, main run. I don't know why GDP is taking so much of time to run, but okay, we will survive. Cool. So now I would be. Oh my! It's just exited. It just exit. Something is off with my machine, I think. But yeah, we'll try to fix it tomorrow. So let's just step over, and here, uh, let's watch chat. So you have entry. Okay. So here I can say yeah, because okay, I get it. I get it. I get it. So this is not initialized. That's the problem. Okay. So that's the problem. So we have to initialize it also. And we're gonna do that. We're gonna do that. So how can we do that? Sorry. Hatch entry should be equal to, but you have to cast a pointer and to say malloc size of entry into the capacity. Okay. So we are here. If we jump over to the next line, and here if we say hat, okay. So now I suppose we have this, and yeah. But we have to initialize 16 of those, I suppose. Have to initialize 16 of those, ain't it? Ah, and here you have to do it in this way. So we run. It's gonna take a while to start the run. That's fine. Oh, okay. Okay. And here I say hash. Okay, it has next. Well, that is not correct. But here, if I say hat of 0, how do you dereference this? Do I have to say it like that? And then like this? Not sure. I am not sure. Okay. Maybe it's time to chat GPT this shit. To spec in GDP at 0, 1. What's the syntax for? Okay. Ah, because it's a pointer of pointer. Got it. The pointer of a pointer. Yeah. I get it. So what is the right way to do it? Yeah, this is I have to do a double pointer. Calloc. What the heck is a calloc? I have never heard of calloc. Ah, okay, the memory is set to 0. Okay. Or debug this live like an algorithm or episode. Okay. Yeah. Let's call it entries. Does this work? Segfault. That makes sense because I don't have indexes yet. So doesn't make sense. It's Maria. Why is it not copying? Okay. So this here would be capacity, and this here would be size of entry. That makes sense. Okay. That makes sense. Okay. Now, now, if that entries equals null, have to return null. Okay. So here, if hat equals null, and printf, I think it is standard error. could not allocate memory. But I also when I execute non-zero exit code. And then here, I'm gonna return zero. Yeah. But we are doing a little bit of memory leak in here because if this is null, if this here is null, we would be leaking this particular memory because this is not null. All right. So, what is the syntax for free? Display, well, not that. Okay. So you just give it a void start nullable pointer. Okay. So I suppose what you can do is free. Well, one of the things I would like to do here is memory leak. I would like to check the memory leak, and one thing I would like to do is with Valgrind. Do I have Valgrind? And how do you use that? Leak check. So I think I can just do Valgrind leak check full at. Okay, what? Valgrind private blah 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 blah. And ChatGPT fixes. Why does it? Oh, React, huh? Man, something is off. One of the cores is spinning. Two of the cores are spinning. What the fuck is happening? What? Something is off with my PC. I'm gonna stop streaming now. I'm gonna see what exactly is going on. And yeah, we'll continue with this effort tomorrow. I'm not gonna continue this effort. There's something definitely wrong here. One, like the two of the cores are completely spinning. I don't know what or what it is running. Yeah, key worker. What are you running? It's not OBS because OBS is taking. Yeah, OBS is here. Okay, cool. I'm gonna close the stream today. Something is off, and I need to check on this part. And yeah, once it's done tomorrow, I'm gonna continue working on this. But for now, I'm gonna stop streaming. Okay, thank you. And multiple cores are spinning up. Am I getting hacked? What the fuck? Okay.